Alrighty, let's go ahead and pick up where we left off. We're on the bottom of page 3 in Module 7, Lesson 7, and we were halfway done with the problem. So we're solving a system of equations. Remember, 2 or more equations is called a system. We did the first one, 0, 3, down 2 over 1, down 2 over 1. Like I said, whenever you're graphing to a plane, you want to put as many dots in as possible. Then it makes it easier to find your point of intersection. So in order to put something on the graph, again, we need to get y alone. So that means do the opposite and move anything else to the other side. So this is going to turn into 3y equals, and then switching the order, a negative 6x and a positive 9, keeping the signs with it. And then the opposite of multiply by 3 is divide by 3, and we get y equals negative 6 divided by 3 would be negative 2x plus 3. So our y-intercept is 0, 3. Our rise over run, whoa, look at this. 0, 3, 0, 3. Negative 2 over positive 1, negative 2 over positive 1. So what do you think's happening there? It's the same line. Look at 0, 3, down 2 over 1, down 2 over 1, down 2 over 1. So tell me about the solution. How many points of solutions will we have? Infinite. Look at this is a solution point, this is, and the lines go forever in both directions. So what we write for that, if you remember from a couple pages ago, is we write infinite solutions along, or on, I should have said on, but along the line. Let's put on, that sounds weird. I don't know where I got that word. I just made it up. So infinite solutions on the line, and what line is it? Y equals negative 2x plus 3. And the reason we have to put that, again, I know I explained it to you before, is because if you just write infinite solutions, that means that's a solution. And this is a solution, and they're not. Only the points on that line are solutions. They're still an infinite number because they go on forever in both directions, but those are the only points that are solutions because the two lines share them. So infinite solutions on the line y equals negative 2x plus 3. So who remembers what kind of system that's called? Remember the little trick I told you? One line depends on the other line. So those are called dependent, or this is called a dependent system. I think Kim used all of her pink ink. What do you think? Well, I'm down to 4 out of 12. I'm getting there. Okay, so dependent, because one line depends on another line because they graph right on top of each other. So if they just ask for the solution, this is the solution. But if they ask for what type of system it is, which they could, that is dependent. Okay, let's go ahead and move to page 4. I think we have one more of these. And there's 3 methods we're going to learn. The first method is graphing. So we're finding the solution by graphing. And I like to start with it because it gives students a visual of what solving a system means. If I started with the algebra, they'd have no idea what solving a system is. They wouldn't realize that it was the point of intersection. So that's why I start with graphing. And then next we're going to start with the algebraic methods, which are more exact But like I said, the graph gives you a visualization. So when you see the word solve and you see two equations, I'm hoping in your head you go, oh, we're trying to find where those two lines cross. And we can even do it without graphing them. Graphing, makes sense. But like I said on the first page, what happens if the solution's 2.17 comma 3.598? How am I ever going to find that on a graph? I can't get that exact. So graphs are fine for whole numbers, but once your solutions turn into decimals or fractions, they're not so good. Okay, let's go ahead and get going on these. So we have another system, 2x plus y equals 3. This is another one that's pretty easy because see how the y is almost alone, the y is alone, so not too much work on this one. So to get y alone, we have to subtract 2x from both sides. 2x minus 2x is 0, so we get y equals negative 2x. And there's no sign in front of 3, so that would be positive 3. So our y-intercept is 0, 3. And our slope, which is our rise over run, is negative 2 over 1. And if you want to stop the video and try and do this one on your own, this would be a good one to practice on. Tiny bit easy, but really good one. So before I put it on the graph and solve the other equation, go ahead, turn it off and try to graph on your own. So 0, 3, and then we're going down 2, 1, 2 over 1, down 1, 2 over 1, down 1, 2 over 1, down 1, 2 over 1. I think I'll put one more. Here we go. I feel like we've had that line before. Was it on the last page? Y equals negative 2. Oh, yeah, it's the same one. Look at that we had here. Funny. Didn't even realize it. Different second line, but same first one. I'm like, wow, that really looks familiar. Okay, so let's get our straight edge. Oh, here we go again. I can't pick it up. So there's our first line with lots and lots of points. So now let's try our second line. So this one is solve for y, but I'm just not crazy about the order. I would rather switch the order. So y is all alone, but it doesn't look like mx plus b. So let's do y equals 1x plus 6. Now it's in y equals mx plus b form. So that's the same thing as 1x, but then it puts a slope there in front for me. And then the y-intercept we usually do last. So this one's y-intercept. X is always 0, is 0, 6. And what would my rise over run be? 1 over 1. Every whole number we write over 1, just like we did here. Well, that was actually an integer, not a whole number. Okay, so we're ready. 0, 6. So the slope is positive, so we go up 1 over 1, up 1 over 1, up 1 over 1, and I go, whoa, I'm not running into the orange line. So that means I need to do the opposite. The opposite of up 1, right 1 would be down 1, left 1. Ding, ding, ding. Because look at this. Down 2, right 1 would be up 2, left 1. So there's my intersection point. We have it. Let's do one more. Down 1 over 1. And see if you can name that point before I do. So first thing I do is I always take a marker and make it big because that is my solution. The solution is the point of intersection. So this would be negative 1 is the x, and my y is 5. And do you all remember from the previous video how I taught you how to check it? So put negative 1 in for x, and 5n for y, and work it out as 2 times -1 plus 5 equal to 3. 5 minus 2 is 3. So if you get a true statement, you go, yay, it works. And then you try it in the next one. So x is -1, y is 5. And so we're wanting to know, is 5 equal to 6 plus -1? Yes, it is. So that's what I love about systems. All three of these packets that we're doing here at the end are systems, and they can all be checked by plugging in your point of intersection and making sure it makes two true statements. Because what that means is the point is indeed on both lines. And that's why we always say you can't just plug it into one, you have to plug it into two, because we're trying to verify that it's a point of intersection, which means it's on both lines. Okay. So that is the end of the graphing method. Method number 2 we're going to learn is called the substitution method. And it uses exactly, we didn't name the system. So this one was called consistent. Remember, if it has at least one solution. Oh man, I hate it when I forget that. Consistent. There we go. So any system that has at least one solution is called consistent. This has exactly one solution. So we name the solution by counting the x, -1, and then counting the y. Okay, back to substitution method. So we'll just go through this example, and then on the next video we'll practice. So notice how both of these are solved for y. That's convenient, right? Well, in geometry, you learn something called the reflexive property. I don't know if any of you remember that. I always told my students, think of a reflection. So reflexive property says that two things are equal to each other. So if this is y and this is y, well, they must be equal to each other, right? Because isn't y equal to y? I mean, anything's equal to itself. So saying that you agree with that y equals y, x equals x, a equals a, you can take, and this is where it gets its name, substitution. You can take out this y and plug what it's equal to in, and then you can take out this y, plug what it's equal to in. So that's why it's called substitution, because we know y equals y, and in place of this y, you're putting its equation, because equal means they're the same, so they can be interchanged at any time. Bring down the equal sign, and in place of this y, we're putting what it's equal to. So that's why it's called substitution, because we're replacing something with something that's equal to. So now you're going to have to think back to chapter 5. Remember how we used to get rid of fractions? We multiplied everything by the LCD, which is 4. So 4 goes here, 4 goes here, 4 goes here, 4 goes here. Why do we pick 4? Because 2 goes into 4 and 4 goes into 4. And we can't skip terms, so we have to multiply every single term. So half of 4 is 2. A positive times a negative would be -2x. And if you're not good with fractions, just type this into your calculator, put an x on your answer. Plus 12 equals, here the 4's would cancel, so you just get 3x minus 8. And again, if you're not good with fractions, just type 3 fraction bar 4 times 4 and you will get that. Okay, so if I do it in my head, that doesn't mean you have to. You can do it on your calculator. But look at that. Beauty! All the fractions are gone. So now I need to subtract 3x from both sides. And then I need this 12 over here, so subtract 12 from both sides. So the 3x's are gone there, the 12's are gone there, so we get -5x equals -20. So x is +4.